So welcome everyone to our class on labs. I'm going to turn off my video since I look pretty rough today. We're technically still on break, so I didn't put on any nice clothes to come to campus today. But I'm going to go here and pull up. It was this one right here. It's basics. Nope, wasn't that one. I lied to you. It was actually Jacob. You were doing this one, the SSH one here, the 136.
Yes, 136.
And I opened it up, and like I said, it worked fine for me, but let's try it again just to make sure nothing weird is going on.
I do not have the, like what you have, like we used to have. I do not have like the blue one that you have on. Because when I clicking on the learning, it take me back to the CCNA, the one. I can't get to CCNA 2.
Jacob, I actually, I put you, that was my fault. I put you in the class today. So you need to go to netacad.com and you will see this class, SRWE.
Okay.
You'll see it now. So that's why. But this is the packet tracer you were having some issues with. And one of the things I could see is, notice how when it first boots up, how that is orange.
Mm-hmm.
If you tried right now while it was still orange to go from the command prompt, so if I tried to telnet here, and it was 10, it's going to fail to begin with, because now see it worked then, but you can see how it went green. We're going to learn about a thing called spanning tree. And whenever you plug in a cable on a switch, or if a switch just comes up, it runs through what is called the spanning tree process to ensure there's not a loop on that particular link. If you tried to do this telnet before that link came up, it would have timed out. But as you can see here, I do have access to it. So once it's up and running, I'll put in the right password. I have access. So we are able to get in here and set up SSH on this particular lab. And that's what this lab is all about. This lab is just about, first it has you telnet in, and then it has you create the SSH. So, you go in and do config, wait a minute, was it class?
So the spanning tree protocol creates that much latency?
Yes, it's up to 50 seconds. It can be up to 50 seconds of latency.
Okay.
When you plug a cable in. If you've ever noticed that, if you've noticed when you plug a cable in and it's amber, it's because of that 50 seconds. Now let me show you something neat here. Actually, let me go ahead and show you. Well, if I can get in, see what my, all right, Cisco. They use Cisco. All right, so I'm in, but let me show you what we could do. This is an interesting thing. I'm going to actually, if it'll let me delete this cable, I bet they won't let me delete it. Let's see. Nope. Okay, let's do this, and let me open up a new one.
Okay, that's what I would like you to do, because I opened a new one.
Yeah, I'm gonna open a new one, and I'll pull out the. I'll actually pull the devices out myself. So let's pull this over here. Let's go and just do. We'll pull out a switch. So we'll grab us a 2960. By the way, I sent an email out today. They have officially announced the replacement for the 2960 is going to be the 1000 series switches. So that's going to be officially announced tomorrow. But all right, so we've got this here. So let's take and let's connect an Ethernet cable from this PC to the switch, and notice how it's in amber mode.
Yes.
Okay. So if I go in here and I'm okay, so I go in here and I do en, I do show int fa0/1. You'll see it says it's up connected, but because it's amber, it's actually going through what is called spanning tree. So show spanning tree. You'll see how this port right now is learning. And so it is in a learn state, not in a forwarding state. So it's not able to forward packets yet. So as long as it's amber, it's unable to forward packets. This is something we'll learn as we move forward. This is that, but you'll notice now as it gets forward, we're now forwarding, whereas before we were learning, now we're forwarding, and you can see it's green. The reason this takes place is because you want the switch, if you happen to be connected to another switch, you don't want it to immediately bring the link up, because there could be a loop. So you have to be very careful with layer 2 loops. We do have a method to make it to where this link will always come up immediately when you connect it. You only put this command, however, on a link that you know is going to be connected to host. It would never be connected to another switch. And that is this. So if I go in global config, I can do interface FA 0/1, which is what I'm connected to. And I can do spanning tree port fast. Okay. And it says this only do this. Okay. If it is not connected to another hub, concentrator, any type of other networking device. Now watch what happens. If I connect the PC to port 01, boom, it goes green immediately. Port fast, this command, okay, that I just put in, tells it to immediately go to the forwarding state when a cable is connected. Don't go through blocking, listening, and learning, which are the other states that can take up to 50 seconds. You would only ever do that on a link going to a host. You would never do that to another networking device. Okay. So, and that's something we're going to learn as we move forward. But if you've ever seen that and wondered why, okay, and you'll notice here, if I go back out here and pull another PC out here, I'll pull another PC out and connect another cable here and go into a different port. This port still has normal spanning tree on it. So it takes up to 50 seconds for it to go through.
No, because so fast port is assigned against a specific port and
Correct.
not the switch.
Correct. It's not a global config. Correct.
Okay.
It's in an individual interface. Now, if I wanted to assign it to all 24 of my fast Ethernet ports, remember what we could do is this. We could do interface range FA 0/1-24. And then now I can do switch port or spanning tree port fast. Okay. Now do right. I now have applied that. If I actually do a do show run, you'll see that under every single one of these now port fast is on. So now any other devices that I connect to this switch, instead of going through blocking, listening, learning, and then going to forwarding, they will immediately go all the way to forwarding as soon as it's connected. And again, we only ever put this command in on a port that is going to a host. Don't ever do this on a port that's connected to another switch or even another networking device. All right. That is probably why you had that problem with that lab. You didn't give it time to come up. So be aware of that.
Okay. Let me ask you another question on the module 1. Where you configure the default, because I tried to use that method on the 1.16 configure the default gateway.
Which one?
1.16. No, in the actual module 1.16.
Which one here? Right here, Jacob.
Which is step 2. They configure the switch. Okay.
Jacob, I don't understand which one you're asking me to look at.
Okay, it's configure the default gateway where you use gateway default 172.17.992. You don't have the same thing that I have.
No, I mean I think you're looking at the other course, because inside of here you'll see we don't have. I mean, here's the labs that we have. We've got the SSH.
Yes, they configure the switch with the internet settings.
Which one of these is it?
The one I go back up again because just say okay. Configure the switch with 1.1.
This one, 117?
Yes.
Okay, so basic switch configuration. Now, here's the thing. This particular lab, remember, if you're doing the physical mode, I want you to be doing it inside of NetLabs. In fact, I have a NetLabs, lab loaded. In fact, I need to go in here because I need to extend my pod here. But this lab really should be done in NetLabs, not in Packet Tracer, because you'll see in our classes, either class you're in, under CCNA 2 right here, basic switch configuration. So I want you to be doing this in here. All right. If you do this lab, okay, if you do the Packet Tracer physical mode, so I'm going to open it up. I'll show you where people are getting in trouble on this one. Packet Tracer physical mode, is set up to do rack and stack. All right, so it's making you have to go in here and actually pull the devices out. So it's telling you, you need to build this. So you'll take your switch, you'll bring it over here. You'll bring your PC over here to work on, okay? And then you've got to connect your console cable. So you're gonna have to actually right click on this and inspect the rear. So you can see the rear of the switch because that's where the console is at. You grab your console cable, connect it to the console port, and then go down here on the PC and connect it to the RS-232 port. Okay. Oops. All right, well then connect to my port here. There we go. Now, then you got to turn the PC on, which is crazy, but you have to. And then go in here on the desktop, and now you'll go to the terminal and open it up just like you were connected to the terminal. Now you're connected to the switch. And so now you're able to do this lab inside of here. So basically that's what it's telling you. From the shelf, drag the switch over, put it in the rack. From the drag your PC over, put it in the rack, connect the console from PCA to switch 1. And where people are getting in trouble is you have to inspect the rear to be able to see the console. Otherwise, you can't pull the cable off and connect it. But once you're connected, then you're able to just go in here and you're connected to the switch. And it says, you know, show me your default, the default configuration. Well, you just go in here and you go, you know, show running config. And then you got like show version, shows you the version. Okay. So this is just in case you don't have real equipment. You all have real equipment. So you can go in here to Net Labs and you can do this lab right here. So you can pick any lab. And by the way, we now have 20 pods available. So we have a large number of pods for you to use. Okay. And so I'm just going to do 33 minutes on this one for basic switch config. And so on ours, we don't actually connect the console cables like you were doing on the packet tracer, because we've already got it connected in our data center. But that's, if you're doing this lab and you want to do this packet tracer, that's how you do it. You have to pull it out here and you have to show the back of it so you can see it. Now, if it's a router, the router has the console is on the front. Okay. I think it is anyway. Nope, it's on the back, but it's on the back too. So they got it back here. So there's, if you want to connect to the router, you have to look at the rear of it so you can see it. You also can zoom in if you can't see it. So if you needed to connect here and you're having trouble seeing it, inspect the rear and then just zoom in so you can see it there. But see, now we've got the cable in, so we basically have got this connection. Now we don't have FA06. So at this point, we would actually have to go here, get this cable, connect it to our fast Ethernet, and then connect it over here to port FA06, which is actually gig 06, 106. Well, here, I'm actually gonna do that and then do 06. Okay. Now we've got that connected. Okay. So now we've got port 06 connected to the PC, and notice how I got, you know, more percentage points. So all of that is available, and then you can go in here and do all your different configurations and things that it's asking you to do. Notice again.
Do you know how to, because it's going to, when do you know how to use that fast Ethernet cable instead of the regular one that we've been using?
Say that one more time, Jacob.
The one that you just did, that you used the green.
Yeah.
When do you know how to use that? I mean,
yeah.
When do you decide to use that one?
Remember, the yellow cable is what's called a straight through cable.
Yes. Straight
through cables are used to connect hosts to network devices. The what I call nasty Carolina blue color, I went to NC State, that's why I say that. This Carolina blue color is what's called a console cable. Okay. So it's a rollover cable that is used to connect only to console ports. So that's just something I know because of the fact that yellow is a straight through and blue is always traditionally a console. Now, out in the real world, I look at them. I mean, you literally have to, you know, let me stop my share a second. Let me pull my camera back up. Okay. And I'll probably have to turn off let me change my video. Oops, sorry, y'all. Turn off my video background. So there, all right, you get to see my nasty office. But you know, in the real world, here's a cable. But if I was out in the real world and I was, even though it was a blue cable like this, now I know this is a Cisco console cable because it's got a console in here, and I can see that. But one of the things I would always do is, even if it's a blue cable, is look at it from left to right, and then look at both sides to determine what kind of cable it is. And so that's just something you have to kind of get used to out in the real world, checking cables, even if they're, you know, if it's a yellow cable, it should be, if it's a Cisco cable, it should be a straight through. But if it's not a Cisco cable, it may not be a straight through cable. And then you may get
stamp collection.
Yeah, those are actually, that's one of my most proud things that I own. That is my father's. How many of you know what a duck stamp is? A waterfowl stamp?
Oh, I know what a duck stamp is.
Yeah. Duck stamps, every year, conservationists and duck hunters buy duck stamps. You have to be able to hunt. And a lot of people buy them just because people don't realize duck stamps are the major source of funding for our national wildlife refuges. That is my father's duck stamp collection from basically every year that he hunted his entire life. So it's got my dad's stamp and his signature on it, and that's federal stamps, and those are state stamps at the bottom. So,
awesome collection.
Yeah, it really is. It goes from 1977 up to I think it was
many years to beat it up.
Yeah, 2014. But here's another cable, and like I said, I would just look at the actual end, and this is, you know, this one tells me this is white, green, green, white, blue, white, blue, green, white, orange, blue, white, blue, orange, white, brown, brown. And on this side, it's the same thing. And so since it matches on both sides, that is a straight through cable. This is a patch cable using the 568B standard. And so you kind of learn how to look at the cables and know exactly what standards are what. That's one of the places where teaching this online is tough for me, because in the classroom, I would be handing all of you cables and would be looking at them, would be plugging them in. This is why this packet tracer physical mode is nice, because it gives us the ability to at least look around at the different cables and use those different cables. Okay. Any questions on that?
Another question I have with the Net Lab, the 1.6, the one that you
this one?
have,
Right, 117? Yep.
Okay. Okay. That one, no, not that one. When I was trying to use the Terra, the instruction asked us to use the Terra, the console in the PC.
Mm-hmm.
And when I tried to, just like I did in the CCNA one, my tenant is not working. And because it just showed me that, and after some time, it said the timeout.
Okay. Now, one of the things I will tell you, anytime you're inside of here, you must use the content right here.
Okay.
Don't use the lab document inside of our curriculum. So if you downloaded this document and you try to use this document with this lab, it is not going to work. You must use the document inside of NetLabs. Notice how this one says this has been updated for use on NetLabs. So just like our last class, if you try to use this document, it's not going to work correctly. So when you're inside of NetLabs, pull up the content right here. Yep. Pull that up, and then I'm going to put this in a new window so I can actually just bring it over here. All right. And so now this is saying configuring basic device settings. And now if you want to go in here, this walks you through. Now notice it talks about the default template. So let's go look and see what the default template is on here. Let's do a show SDM prefer. You'll see this one already has the dual IPv4, IPv6 loaded. So you don't have to redo this particular template. So this one's already done. So if you're looking at this part where it's telling you to actually do that, you don't have to do it because it's already enabled. So let me pull this over here and pull this lab up over here. All right. But at this point now we could go through here and it says, you know, show running config. So we go in here and do a show running config. And it's going to ask you how many fast Ethernet ports are there. Well, one of the things I'll tell you, you could look and it's say 1 through 24, and there's 2 gigabit ports. Another thing you can always do is this show IPent brief, and it will tell you very quickly all the ports. Okay, so it shows you there the ports that are available. All right. And it says, what are the range of values for the V2I lines? Well, if you look up here, it's 0 to 15 for the V2I lines. So they're just trying to get you to look through all the different parts of the switch. And then these, you know, those are where you put your answers in here. Now watch this. This is interesting. Let's look at this. Let's do a show VLAN. You'll notice that by default, there's only one VLAN. And that's an important thing because all ports are in that VLAN, which means if you connect 2 PCs to ports, they can talk to each other. They can see each other. All right. You also will see here, if you do a show interface VLAN 1, you'll see that there is an interface, but it is down. All right. Now, a lot of people go, why is that down when there's a cable plugged in? Well, take a look here. If we do a show IPent brief, you'll notice there's no up port other than VLAN 1. So there's no physical port in VLAN 1 that's up. So for that reason, the protocol is down on VLAN 1. Now let's go to port FA06, and the lab has you do this. The lab has you go into interface FA06, do a no shut command. Now let's watch what happens VLAN 1 now. Notice how now it's down, but it'll come up in a second. It's down because the it's going through spanning tree. Control Z. Do a show IPent brief. All right, should be coming up. Now it's up, down. Should come up. Eventually will come up. There it went. So now it says show IP, show int VLAN 1. You'll notice that VLAN would not come up until there was a physical port in the VLAN up and running. All right, which is very, very important.
I just wonder exactly what this VLAN means. That means the collect the family of all port or the virtual something.
It's a virtual local area network. In fact, this is a good place for us to come over to what I was going to talk about a little bit today, and that is this. Let's have a little bit of a history lesson. Okay, so we're looking at virtual LANs. So we're looking at VLANs. All right, so VLANs. Now that is virtual. Keep hitting the button. Sorry, y'all. Let me move this button around where I can't hit it. Virtual local area networks. Now I just showed you a switch. What VLAN what VLAN are all ports in by default? Okay, so we just saw that. We were just hearing a switch.
VLAN 1?
VLAN 1, correct. So if I do a show VLAN, you'll see that by default, all ports are in VLAN 1, which means that by default, all of these ports can see one another. When traffic comes into a switch, it gets tagged with the VLAN it is associated with inside the switch. All of these are associated with VLAN 1. Now, let me show you this. Back in the old days, everybody remember this? This was our old Ethernet. This is just our standard old Ethernet. We've got a PC here, PC here, PC here, and a PC here. So it's all Ethernet, right? A, B, C, and D. We had terminators on each end. Anybody ever work with RG58, 59 cable and actual true bus networks? Okay. Well, remember how we had carrier sense, multiple access, collision detection. So in other words, A wants to send something. So A is going to say, all right, I'm going to look on the line to see if it's clear. If it is, I'm going to send. That's the carrier sense. Multiple access, because all devices can look and see it's clear at the same time and send and cause collisions. But what would happen with this is when A, let's say A was sending to D, obviously in that frame, there would be in the header, remember in the frame header, there's going to be a destination MAC address, DST MAC. Y'all remember this? And a source MAC. Remember all that, right? Source MAC?
Yes, yes.
Okay. So in this frame, there would be a destination MAC address, which would be D's MAC address, and the source MAC address would be A's. Well, it would come down here on this line and come down here. It'd go both ways. It'd hit the terminator and go away. It'd come down this way. B would pull a copy off and look at it and say, "Ooh, that's not my MAC address," so it'd throw it away. It'd keep coming down here all the way down to C. C pulls a copy off. "Oop, that's not for me." Come down here to D. D pulls a copy off. "Oop, that's for me," and would then take the frame apart, run the CRC, pass it up to layer 3, right? And it would still continue down here and hit the terminator and go away. Well, obviously, one of the issues we had is as you added more devices, okay, so let's imagine we keep extending this line and add more and more devices off of here, the possibilities of collision become much higher. You agree with me? Because somebody's going to look and see and send, and you're going to have a collision. So the longer the segment became, the more chance of a collision would take place. So we developed these things called bridges. Okay, and this was a symbol for a bridge. And with the bridge, what we would end up doing is this. We would still have over here A, B, C, and D. Okay. And on this side over here, you know, we put E, F, and G. So let's put our A, B, C, D, E, F, and G. Okay. So now what would happen is this. This device, by the way, it was called a bridge, but what it really was a 2-port switch. That's all it was. And it would build a MAC address table, and it would say, okay, on port 1, I'm going to learn the MAC addresses. By the way, it would have to look at this just like a switch. It would look at the incoming source MAC addresses and put that in here. So if it saw a frame come in that was a source MAC that it didn't know about, but it come in on port 1, it would put it into the table. So eventually you would have over here A MAC, you know, B's MAC, C's MAC, and D MAC. They would all be known on this side. And F MAC, F's MAC address, G and E's MAC addresses will all be known on this side. So what would happen if A sent something to D, it would come down here and B would still have to look at it, C would still have to look at it, D would get it, it would get to the bridge, and the bridge would go, well, the destination MAC address is already on this side, so it would drop it, it would not forward it. So a bridge was our first switch. It was just a 2-port switch. So what is a switch? Well, a switch is simply a multi-port bridge. So in other words, we've got a MAC address table, right? So here's our ports and MACs. So what we end up with is every single port on the switch, okay? So 1, 2, 3, and 4, it learns the MAC addresses of the devices off of that switch. You with me so far? Everybody understand what we're doing here? Let me ask you this. What does a switch do with an unknown MAC address? So a frame comes in from an unknown MAC address. All right, so it comes in here. What's this switch going to do with it? By the way, the symbol for switch is this. It forwards it out every port except for the one it came in on. That's what a switch does with a frame that it doesn't have a MAC address in its address table. Okay, so it forwarded out everyone except for the one that came in on, because it assumes, because it's an old, you know, it's still a bridge, still thinks it's a bridge. It assumes that if it come in on that particular link, then if the MAC address is there, it would know it. So it doesn't forward it back out that same one. But what we ended up doing is this. Everybody said, oh, that's great. We now have collision domains. By the way, this is what this becomes. These become two collision domains. There's a collision domain on the left, collision domain on the right. On a switch, every single port becomes a collision domain, so it's micro segmentation. But we still had an issue. And that issue was this. We said, people decided, they went, well, you know what? That's great and dandy. We got these switches in our classrooms. We got these switches in our buildings. All right. So here's a switch. All right, sitting in the classroom. And here we have a faculty PC. Okay, so this is faculty. And then here we've got 3 student PCs. I don't know about y'all, but do students do nefarious things? Do you think if a student was able to grab the exam and look at it early off the instructor's machine, they would do it?
No.
Yeah, most of them would, okay? So what they decided is, by default, all these are in VLAN 1, so all of these can access one another. But they didn't want that to happen. They wanted a way to virtualize the local area network, okay? Now, one option is this. We literally do the following. We buy another switch, okay? So here's a switch that's only being used by faculty. Here's a router up here, and we put the students on one side, and we put the faculty on another. Now, at this point, using routing processes, we could keep the students from being able to see what's going on the instructor's PCs. What's the problem with this method? Can anybody see a problem with this method?
You have to remote into 2 different switches to control the network.
You got it, exactly. You got to remote in 2 different switches. And the key point was you got to buy 2 different switches. So that was a cost prohibitive thing. Also, imagine this, if you had a building, and that's the example used in the curriculum, there's a building with different floors, and you got an HR person up here on the 5th, on this top floor, and an HR person on the bottom floor, and you want all those folks to be in the same network, you would have to buy an HR switch for every single floor. Well, that's not going to work out. So what they did was this. They said, let's figure out a method to where we can tag the traffic in a switch so that inside the switch, we can virtualize the local area network. So we're going to make it appear that each port is actually on a different network. So we're going to create VLANs. We'll create one VLAN named 10. We've already got one. Everybody's in one. We know that. And so we'll make that our faculty VLAN. So that's going to be a faculty VLAN. Okay. We'll do another VLAN that's 20. We'll make that students. And what we're going to do is we're going to go in here and we're going to say, okay, ports 1, 2, and 3. By the way, I'll just use this as we'll say this is the red VLAN, even though it's not really red. They're going to have the faculty PCs on them. So there's, that should have been okay, faculty PC, PC, PC. So there's faculty PCs. Okay, and maybe a faculty server. Then we're going to go over here with the blue VLAN, which is VLAN 20, and we're going to create these ports. All of these are going to go to those nasty students, which I do know we have to have students to stay in business, y'all. Okay, but what happens in the switch is that when traffic comes in from these, it gets tagged either blue or red, and they do not mix and match with each other. In other words, you literally have a virtual 10 LAN and a virtual 20 LAN. You can even put PCs on the same network, but if you put one in VLAN 10 and one in VLAN 20, they will never communicate with one another, because another way to look at these virtual area networks is each one of these is a different subnet. So each one of these would be a different subnet in addition to being a VLAN. Are you with me so far? So here's my example I give students. Take a chainsaw, cut your switch into 2 different pieces. And that's literally what we just did. We cut this switch into 2 separate pieces. It now supports a VLAN 10 and a VLAN 20. They cannot, on a layer 2 switch, that's what this is right now. This is a layer 2 switch. You cannot get from one VLAN to the other without the use of a router of some form of fashion. So let's run back over here real quickly. I want to show you something. Let's run over here. That's basic switch configuration, so we don't need to worry about that one. Let's go to this one. Let's go to my inner VLAN routing. Okay. So I'm going to request more time here. By the way, if you ever need to request more time, you can. Now let's take a peek at this. Actually, I'm going to pull out a packet tracer because I'm going to do a quick example. When it comes to speed, packet tracer is a little quicker. The fidelity is off, but it's quicker. All right, so I'm gonna take a switch here. Whoop, not a cloud. I'm gonna take a switch, pull a switch out. I'm gonna pull out two different PCs, here and here. And I'm going to, since we're gonna show you first, so I'm gonna show you first. All right, we're gonna go fast Ethernet. Ooh, what in the world did I grab here? Grab the wrong cable. We're gonna grab a straight through cable connected to 0-1. Notice it's going through spanning tree. I hadn't fixed that. Go here, here. And I'm going to put these two on the same network. So let's put the IP address 192.168.12.10. Y'all know that's just because that's my favorite. /24. Then I'm gonna go over here. I'm gonna make this 192.168.12.11, 192.168.12.11. And there's absolutely no reason I use 12 other than the fact I just like it. Okay. And so now doing IP config, you'll see that we've got 192.168.12.11. I'm going to ping over to A 192.168.12.10, and it works. Okay. I can also go to the switch, and under the command line, you can see show VLAN. You'll notice every port is in VLAN 1. So now I'm going to create VLANs. By the way we create VLANs is very simple. We create the VLANs, then we put ports into VLANs. So we're going to global config. We'll type VLAN 10 and give it a name of faculty. I'm going to do VLAN 20. Give it a name of students. And we'll type exit. And you'll notice here, if I do show VLAN, you'll notice I've got these two new VLANs, but no ports are associated with them. So nothing's changed at this point. I can still just ping easily from PC1 to PC0. No problem, because they're still in the same VLAN. And now what I'm going to do is I'm going to go and I'm going to put interface FA01, and I'm going to do switch port mode access. That turns it into an access port, which means it can only be part of one VLAN. And then switch port access VLAN 1. And that'll put that, excuse me, not VLAN 1, VLAN 10. That'll put that into VLAN 10. Hit up arrow a couple times, go to port 2. Hit up arrow a couple times, oops. Make it an access port and put it in VLAN 20. Now if I do show VLAN, look what happens. Port 01 is in VLAN 10. Port 02 is in VLAN 20. Now, out here on this link, you'll notice it also goes back through spanning tree because they went into a VLAN. But out here on this link, nothing is happening. There's no difference. PC0 has no idea it's even on a VLAN. But when the data comes into the switch, it gets tagged with the VLAN ID. And because of this VLAN ID, only devices on VLAN 10 can talk to one another, and only traffic from VLAN 10 can go to ports in VLAN 10. So if I go back over here now, they're both back up. If I click right here, even though they're in the same network, I cannot ping PC0 anymore. Because for all intents and purposes, these two devices now exist on two completely separate virtual local area networks. One is on virtual local area network 10. One is on virtual local area network 20. They cannot get to each other because they're not physically connected to one another. How would I fix this? Well, one is I could put a router in and I could route between these two VLANs. Or I could just move port 02 into VLAN 10. So let's do that. Let's go back in here. and let's put port 02. And let's put it in VLAN 10. So we're going to move it back over into that. If we do show VLAN, you'll notice now ports 01 and 02 are in the right VLAN. Now it'll go back through spanning tree again. So it won't immediately let me ping because it's going back through spanning tree. How could I fix that to keep it from going through spanning trees? Anybody remember what we did at the very beginning of class? We put port fast on here. Okay. We put port fast on it, and then it would immediately pop into that. But now notice what happens. Now I can ping again. If I do the right thing, I can ping again. Because these two devices, PC1 and PC0, are in the same virtual area network. They're in the same VLAN.
So the VLAN is pretty much an additional layer, like a probably layer that to subnet.
Yep, it's a layer 2. It's still layer 2, but what it is, it's called a .1Q tag. Okay, if you've ever heard of .1Q, it's a .1Q tag that gets added to the frame. So basically, in that frame header, you get your frame header with the destination and source MAC. There's a little .1Q header here that lets you put in your VLAN ID. So your VLAN ID goes in here as a .1Q tag. So when the frame comes in, and again, it's kind of wrong to show this as blue and red, because out here, there's no tag. But as soon as the frame comes into the switch, if it's on VLAN 10, then this is tagged as VLAN 10. If it comes in, it's on VLAN 20, and that's how they keep them separate from one another. If a broadcast comes in, it gets tagged as part of VLAN 10, it would go back out all of these VLAN 10 ports, but it will not go out the VLAN 20 ports because it is associated only with that VLAN. So it's called a .1Q tag. We used to have another type of tagging called ISL, interswitch link. Nobody uses that anymore. .1Q is what we use. You probably may have seen it written like this, 802.1Q. That's the actual specification for it, 802.1.Q encapsulation or tagging, but we call it .1Q tagging. So it's a additional layer 2 item that's added into the frame header as part of it.
Can we safely say this VLAN is a kind of is primarily designed to manage the so-called collision? Can we say that, or there's additional usage?
I think you can say that it helps reduce. Well, it doesn't really deal with collisions. It's used more for security, but I will say it does help with some performance issues, because instead of having all these ports on one network, one LAN, you now have 3 PCs on a VLAN and then these all other PCs on a VLAN. So they won't affect each other traffic wise. Switches themselves help with collisions. VLANs are used more, honestly, for separating traffic for security reasons and for traffic shaping, more so than just for creating collision domains.
What's going to happen to this speed?
So what?
On VLAN 10 and are they going to have similar speed?
Yeah. I think, are you trying to say they're like they have the same language? Or what was the, say that again, one more time. Any questions? Now, in the curriculum, it goes over the .1Q tagging, and it talks about how, so I can find here it is. It goes over inside of here, VLANs, and it talks about what a VLAN is, types of VLANs, here again, it's showing a building, benefits of VLAN design, because you can see here, we've got actually VLAN 10, 20, and 30. For instance, one of the things we do in the real world is we almost always have our wireless networks now today on their own VLAN. And in fact, we'll usually even have multiple wireless networks that are multiple VLANs, with a guest VLAN for wireless being a different VLAN than our normal wireless VLAN that we use. So you do get, again, smaller broadcast domains. So it is a smaller broadcast domain, not necessarily collision domain. But you do get a lot more improved IT efficiency because you don't have to go buy multiple switches. You can just break the ports up as you need and as they are in use on your network. So let me see if I can find multi-switch environment. One of the things that's important to note in a multi-switch environment like this is that VLAN tags have to be maintained. You notice I put on the port here, I put the command switch port mode access on the ports that were being configured to connect to the PCs. Well, access ports can only be part of one VLAN, except for in the real world, we do have a thing called a voice VLAN, which they've kind of used to modify that so that a port can be both in a voice VLAN and a data VLAN. But other than that, it usually is only in one VLAN. But then we have to be able to maintain those tags across the switches. If the tags are removed, well, when the frame got over here to switch 3, it wouldn't know what VLAN it belonged to. So that's what is meant by a trunk. As you read this week and as you're doing your labs about trunks, a trunk is simply a link that maintains tags and allows those 802.1q tags to travel across to other switches. So in this instance, we would have to be trunking from S2 to S1 and S1 to S3. Otherwise, we would lose our VLAN tags and the faculty PCs would not be able to communicate with each other, and the student PCs and the guest PCs would not be able to. So you'll notice here, if we had no VLANs, look what would happen. If a broadcast went out, everybody would see it from the faculty. But with VLANs, we don't have that. With VLANs, it comes in, that broadcast is only going to go out to members of VLAN 10, because when it comes in switch 2, that broadcast would have been tagged with the 802.1q tag as part of VLAN 10. And here's the tagging. So again, it's that one, it's a little 802.1q tag, and it's got our VLAN ID, 12-byte VLAN ID right here. It goes right after this source destination MAC, right before the type link. We put a little tag in there.
So trunking is only there to support the, I guess, the delivery of the tags?
Correct. That is correct. Yep. The trunk is there to allow those tags to be maintained between switches. That is exactly right.
Okay, that's just wow. That's news.
Yep. That is the reason. All right. So any other questions? Let's go back and look just for a second at this lab. The first lab, our VLAN lab, configure VLANs and trunking. Let's pull the content up. Remember, we've got to use this content. If we don't use it, it will not work. So we're going to put this here, and then we're going to pull this out and put it over here. So we got that here, here. Stop it. Thank you. All right. So basically, we would do a basic config of the switch. So again, that's something we should be able to do. Just click on the switch, go into it, hit enter a couple times. Config T, config T, host. Oh, what we got here? S1. So S1. Now, one of the things I do is I do this. I go line con 0, logging synchronous. I do that almost the very first thing. Password Cisco login line VTY 015. Okay, don't know why that did that. Line VTY 015, and I don't think we're not doing SSH on this, are we? Nope. Okay, so we'll do again, hit up arrow a couple times because I'm using the same password. Login, enable secret class, and then no IP domain lookup, no IP. Actually, this is, this version does not have a hyphen. And then we got to do IP addresses for VLAN 1 on each switch. So then we just go in the interface, VLAN 1, IP add 192.168. 1.11.255.255. You shouldn't technically have to do a no shut, but I always do a no shut anyway, just for poops and green. Do right. And at this point, we would be ready to go as far as that basic switch. Now, if I wanted to create a new VLAN, how would I do that? What's the command? So right here, it's showing you how to create the VLANs. So we go into global config. All right. We go VLAN 10. Name operations. VLAN 20. Name. By the way, you don't have to bark it. You don't have to back out of these. Parking lot. And the reason they call this parking lot is because, believe it or not, VLAN 20, then hit enter. I tried to do both. It used to be, there was actually, believe it or not, the old iOS would let you create the VLAN and name it at the same time. I wish they still let you do that, but they won't let you do that anymore. And then VLAN 30.
99.
Oh, is it 99? Oh, sorry. VLAN 99. Name management. Thank you.
And 1000.
All right. VLAN 1000.
Native.
So now if we do a do show VLAN, you'll see those. Now you don't see 1000 yet. And this is a very important thing. Until you actually exit from the config VLAN, the VLAN is not created in the VLAN.dat file. Now, as soon as I exited, you'll notice it got created. So when I actually moved from VLAN 10 to VLAN 20, operations was created. And when I moved on down, the native was not created until I exited. That's a major difference between Packet Tracer and the real world. Here in Packet Tracer, you'll notice config T. If I go in here and do a do show VLAN, you'll notice that I've got 10 and 20. If I type VLAN 30 name test, all right, do a do show VLAN, look what happens. See how that shows up right there? It's automatically added, even though in the real world, that does not happen. And I've seen people get in trouble with that. So for instance, let's do this again. Let's do a VLAN 45 name test. Okay. Now do show VLAN. You'll notice VLAN 45 is not there yet. All right. It is not added automatically on a real device. You have to exit from this config mode. And then as soon as you do, lo and behold, VLAN 45 shows up.
Okay, so Packet Tracer writes it direct to
Right.
the config, where real world, until you commit, it doesn't get written.
Well,
and
and
the
here's
exit
the-
is the commit.
Yep. And here's the thing. It's not being committed to the config. It's being committed to a special file. Remember, it's actually being committed to this file vlan.dat. There's a special file on the switch, and that's where your VLAN information is stored. Is here. Because watch this. If I do a show running config, okay, let's look in here. See if you can see anything that says VLAN on it. There's nowhere other than the interface VLAN. There is no mention of a VLAN at all on this switch. See that? Now, if I do a show VLAN, yeah, we've got 10, 20, 45, 99, and 1000. But that's because that's not being stored in the startup or the running config. It's being stored in the vlan.dat file. And that's one of the quirky things about VLANs and about switches. That file is very important because that file holds your VLAN information. Now, just because I created VLANs, they really at this point are having no effect whatsoever on this switch, because now we need to move ports into those VLANs. You'll notice here they're going to take and make port 06 an access port and put it in VLAN 10. So this basically says make it an access port. So it cannot be a trunk. It's an access port, and associate it with VLAN 10. And that's the one VLAN it's going to be associated with.
Okay, so the DAT file is essentially a roadmap, but until you configure ports, there won't be any
Correct. Yep.
associated.
Yep. You've got all your VLANs made here, and they're stored in the vlan.dat. Now, what is important is this: if you go in here and you do interface FA06 and you do switch port mode access, and then you do switch port access VLAN 10. Okay, and then we'll do a do show run. You'll notice this does go into the config. So it does, the actual port assignments do get put into the running config and the startup config if you do a copy run start. But the VLAN information is stored in that VLAN.dat file. Where people get in trouble is when the VLAN.dat is destroyed, or a port is a port, or a VLAN a port is associated with is removed. So for instance, let's imagine this. I'm gonna do this right now. I'm gonna do a no VLAN 10. Do show, and I got it. Actually, do show VLAN. Okay, so there's no VLAN 10, but I put a port in VLAN 10, right? So do show run. You'll see this port 06 is supposed to be in VLAN 10. So look what happens to that port when I do a do show int FA06. It's up, but if you were able to see the front of this, it actually would be amber right now, because yeah, let's do this. Let's do 6. There it is. Now it's failed. Do show. Yeah. I can't go back there right now and show you, but if you were to actually go look at this port right now, it's connected, but it's actually amber because it's part of a VLAN that doesn't exist. It's called an orphaned port. And they mention that in the curriculum. They mention what's called an orphaned port. So make sure you don't accidentally orphan ports. If you want to get rid of a VLAN, what you need to do is put the switch back in the default VLAN, which is VLAN 1. So now if I do a do show VLAN, you'll notice that port 01, or excuse me, 06 has now gone back to VLAN 1 because I took it out of VLAN 10. All ports will be part of VLAN 1 by default unless you move them. That's why they've got this thing called a parking lot. And a security best practice is to actually move all of your ports out of VLAN 1 and put them in a parking lot VLAN so that they are able to not be accessible if somebody just plugs a cable in.
Because this VLAN since is for switch.
Correct.
For routers, we don't have it, right? Do we?
Right. Correct. Routers do not have VLANs. Nope.
Okay.
Now we configure. We're going to have an entire chapter where we talk about how to configure your routers to support the VLANs on your switches. Okay. But we do not create VLANs on routers. That is correct. Any other questions before we call it a day? Any questions?
Yeah, I have one. So if you have a network across a campus or something, if you have one building a VLAN 10 and a different building VLAN 10,
yeah,
you would use the trunking to connect them, or would you do that with a router? That does depend on distance.
Okay. Here's what's happened. Let me kind of show you the way network design has changed over the years. So let's imagine this is a campus. All right. And so here's a building, whatever building it happens to be, here's a building, and then here's our point of presence, or where our main data center is. This is our main data center. Okay. It used to be that we'd take our switches here. All right. And we would home run, or we would go back to the data center and we would trunk here. Okay. And we do the same here. So we'd have a trunk here. And so our VLANs would be campus-wide VLAN. So if this was VLAN 10 over here, then a PC over here on VLAN 10 would be in the same exact VLAN. All right. The problem was, if a broadcast goes here, it would go through every one of these buildings. So this was called a flat, layer 2 network. A layer 2 network. And the reason being, obviously, layer 2 is what was extended out to each one of our buildings. Okay. Well, we said, that's a good way to do things, but we've got a better way to do it. So what we're going to do, instead of doing that, we're going to have our central point of presence here. Okay, so there's that building. And we're going to have this building here. We're going to have a building over here. Okay. In each one of these buildings, we have switches, obviously. Okay. Now, we also have what's called a multi-layer switch, which is a switch that can do layer 3. So now, instead of trunking, we actually route. So this is a routed link. So this is now a layer 3 link. Okay, that lets us do things like summarize this building. It also allows us to put our VLANs so that our VLANs are specific to the buildings themselves. So VLAN 10, 20, 30, 100, whatever. Over here, you know, same thing. We have a routed link to a multi-layer switch. So now this is layer 3. It's not layer 2. And over here we have VLANs. Now we could have another VLAN 10, but it's not the same VLAN as what's over here because each building is its own, basically, layer 2 domain. The good news with this is it keeps from having broadcast propagate across our entire network. So this is it's not really called, it's basically called a layer 3 network or layer 3 campus design. Okay. So that you're running layer 3. And this is what we're doing at Stanley. We used to do the layer 2 design, but basically now we have a main building. And then from each one of those, we have literally just a /30 that's going over to the building. And, you know, and each one of those, and then inside the building, we have our own VLANs. So STP, you'll learn about spanning tree, is running locally only inside the building. You know, and your VLANs are only significant inside the building. Having said that, you may run into on a major and a large campus, the wireless LAN controllers and devices that create, they actually create kind of like a tunnel. So they create a tunnel that comes across here, and that tunnel allows your wireless traffic to come across and appear to be all on the same VLAN. Okay, so that's something that's out there that, you know, you may see that may confuse you a little bit. So you may actually have a VLAN, you know, 200 that's your wireless VLAN for all your instructors or for your secure instructors, and you may have a guest VLAN that's you know, a 200 or 300, and those are actually maintained campus wide. But you do that by creating these tunnels that allow you to tunnel across these layer 3 links. Does that make sense? Does that help? So we used to do this. We used to have full layer 2. Okay. And so we'd trunk out to each one of our buildings. And so broadcast could actually affect the entire network. They could actually travel all the way across between buildings. As traffic increased and as we had more and more problems with being saturated with broadcast, it was decided a better way to go would be to have a routed network design to where we use layer 3 connections between buildings and just keep our VLANs inside the buildings as being significant. Okay. Any other questions? Very good question. That's a really good catch there, because the change that's been fairly recent. I mean, that's been in the last 10 years or so that we've made this change, maybe 15, but last 10 to 15 years that we've made this change from a layer 2 design all the way out to our edges to a layer 3 design to our edges now.
Okay.
We have assignment that it can help us to practice everything that you are talking about today. Because it's a good lesson that somebody needs to practice with.
Yes, and that's on the labs that have been assigned for this particular chapter. So our labs that are in the syllabus. So for this week, you should be working on, you should be working on right here. Do 1 or 2 of these packet tracers and then do these labs. So you're working on those labs right there. Okay, because those labs are our labs on creating VLANs and inter VLAN routing. And we'll talk about that some more on Monday. Okay. Any other questions before we call it a day? Thank you, everybody, for being here. Excellent number of folks in class. So it really helps to make things easier for me instead of just having to listen to myself out. It's nice to have a group to kind of bounce ideas around on.
Thanks, Kelly. Appreciate your time.
Thanks, everybody. Have a great day, and I'll get this recording out to you shortly.
Have a great weekend.
You too. Take care, everybody.
Bye.